Good morning, students. This session is for class 11th. Students, in last session we have completed the topic that is work done by variable force. Okay, and we have derived the formula for work done by variable force, that was integration from initial limit to final limit f dx, where dx is the very small displacement in which we took the force as constant. Students, in this session we are ready to understand the concept of conservative and non-conservative forces. So let us discuss this topic in detail. You can see the conservative force on your screen. So let me read the passage given about the conservative force and I will explain you about this force in detail. Okay, so let's see. A force is said to be conservative if work done by or against the force in moving a body depends only upon the initial and final position of the body and not on the nature of the path followed between the initial and the final position. So student, if the nature of work it depends only upon the initial and final position but not depends on the path, so the work done by the forces are known as conservative forces. Okay, or such type of forces are known as conservative forces. So this means work done by or against a conservative force is in moving a body over any path between fixed initial and final position will be the same. So if final and initial position is same, then if you follow any one path, work done in along each path will be same, because work done due to conservative force it depends only upon the initial and final position. Okay, so if this one is initial position, this one is final position, so if you move along this path straight line or along this path or along this path, work done in each of the cases are same. Now we are able to see the examples of the conservative forces, that are gravitational force and is a conservative force. You can also write the electrostatic force is also conservative in nature. So let us see the properties of conservative forces. So you can see here, work done by or against a conservative force in moving a body from one position to the other depends only on the initial and final position of the body. So you can see it does not depend on the path followed by the body, but it only depends upon the initial and final position of the body. So you can say in other words, these are not path dependent but these are point dependent functions. Okay, so this one is one of the most important property of conservative forces. Second one is work done by or against a conservative force does not depend upon the nature of the path followed by the body in going from initial position to the final position. So we have already discussed about this point, but this one is also one of the property of the conservative force, so we should understand this property also. So we can see here, the work done by or against a conservative force does not depend upon the nature of the path followed by the body in going from initial position to the final position. Okay, so this one is the property of conservative force. Now we are ready to understand the third property, and that is work done by or against a conservative force in moving a body through any round trip. Round trip means we are talking about the closed path where final position coincide with the initial position of the body is always zero. So let me repeat, this point is very interesting and very important. Work done by or against a conservative force in moving a body through any round trip. Okay, so round trip means you can say a circle or you can say a circular path. So the work done by or against conservative force in moving a body through any round trip means closed path where final and initial points are coincide with each other is zero. So In this case, the total work done by conservative force is 0. So I hope you understand the concept of conservative forces and their properties. Let me repeat, what is conservative force? You can easily say, if work done is independent on the path but only depends on the initial and final position of the body, then work done by the forces are known as conservative forces. Properties, you can say these are the point dependence but not path dependence, and in on any closed track the total work done by the force is 0. Closed track means if initial point and final points are coincide at same point, then we can say that type of loop is a closed loop, and in that type of loop the net work done by force is always 0. So these are some properties of conservative forces. I hope you understand. Let us now study about the non-conservative forces. So you can see here, a force is said to be non-conservative if work done by or against the force in moving a body from one position to another depends on the path followed between these two positions. Okay, so these type of forces are known as non-conservative forces. Let me repeat the statement. A force is said to be non-conservative if work done by or against the force in moving a body from one position to another depends on the path followed between these two points, or you can say these two positions. So you can say this one is the reverse process of the first one. In this case, you can see the work done by the force is path dependent. Okay, so if between any 2 points path are different so work done in that case along each path are different. So these type of forces are known as non-conservative, and they are always path dependent forces. Examples: frictional force is non-conservative in nature. So you can see frictional forces are non-conservative in nature and they are path dependent. If path is between any 2 point path are different, then the work done by the forces are different. Okay, let us study the power. I hope you know what is power, but let me give you the basic information about power, and then we will study about the average and instantaneous power. So let's see. Power of a person or machine is defined as the time rate at which work is done by it. You can say the rate of doing work of a person or a machine is known as power. So power is defined as the rate of doing work, that is work done upon time interval. Okay, so thus power of body measures how fast it can do the work. So more powerful person can do work very fast, and if power is less, it means a person or machine can do work slowly. So it means power measures how fast a machine or person can do work. Okay, so it is mathematically given like work done upon time interval. Now you can see the formula. This is the formula: P is equal to dW upon dt. This is the formula for instantaneous power. Okay, this one is the formula for instantaneous power. So power is given by P is equal to dW by dt. You can see here, this is the formula for instantaneous power. Okay, now since dW is equal to F dot ds, this is the formula for scalar product of the work. For very small work, you can write dW is equal to F dot ds. So you can substitute this value of dW in above equation, and you will get P is equal to F dot ds by dt. Now this ds by dt will be V, so you will get P is equal to F dot V. Okay, so you can write P is equal to F dot V. You can see from this equation that power is a scalar quantity because it is resultant of scalar product of force and velocity. Okay, now you can write down the dimension of power. So dimension of power can be found by the formula P is equal to W by T. You can see here. Now W is equal to M L squared T to the power minus 2. This is the dimensional formula for work, and this T is the for time. So it is M L squared T to the power minus 3 finally. So this is dimensional formula for power. Now unit of power is, so the absolute unit of power, that is SI unit, is watt, and you can write a unit of power in terms of unit of work and time also. So 1 watt is equal to 1 joule upon 1 second. You can see 1 watt is equal to 1 joule per second. Now you can also define 1 watt of power, and it is power of body is said to be 1 watt if it can do 1 joule of work in 1 second. Okay, so it is important definition of 1 watt power. This is power of body is said to be 1 watt if it can do 1 joule of work in 1 second. And there is another unit of power, that is horsepower. So 1 horsepower is equal to 746 watt. So you have to remember this formula if power is given in horsepower. So to solve the questions, you must change this horsepower into watt. For this purpose you have to remember this relation, that is 1 horsepower is equal to 746 watt. So try to remember this formula. This is very important definition of 1 watt, and this is relation between horsepower and watt. Okay, now let's see what is energy. So you can see here, energy of a body is defined as the capacity or ability of the body to do work. Okay, so this is the ability or capacity of body to do work. If a body have high amount of energy, it means the body can do more amount of work, and if body has less amount of energy, it means body can perform less amount of work. So energy is measure of capacity or ability of work that can be done by the person or machine. Okay, next point is kinetic energy. So the kinetic energy of body is energy possessed by the body by virtue of its motion. For example, first one is a bullet fired from a gun can pierce through a target on account of kinetic energy of the bullet. You can see the examples of kinetic energy, and you can note down from the screen. Okay, so pause this video and try to note down these things which is shown on the screen. First one is the bullet fired from a gun can pierce through a target on account of kinetic energy of the bullet. Second one is windmills work on the kinetic energy of air. For example, sailing ships use the kinetic energy of wind. Third point is water mills work on kinetic energy of water. For example, fast flowing stream has been used to grind corn. And fourth one is a nail is driven into wooden block on account of kinetic energy of the hammer strike the nail. Now we are ready to derive formula for kinetic energy. So we can use different methods. For this purpose, let us assume the following things. Suppose m is mass of the body and u is the initial velocity, and f is the force applied on the body. Okay, a is acceleration produced in the body in the direction of the force applied, and v is the velocity acquired by the body in moving through a distance s. Okay, So here you can see this is the object. Okay, suppose initially this object is in rest. After applying this force and after some time t, its final velocity becomes v. In this time interval it travel a distance s. So you can use third equation of motion. Actually this equation is v square minus u square. V square minus u square is equal to 2s. From this relation you can use the value of u, that is 0. You can see here the value of 0. So this becomes 0 and v square is 2as. So finally you get a is equal to v square. This is actually v square upon 2s. This is the value of acceleration. Now the force is defined like this: F is equal to m into a. So substitute the value of a here and you will get F is equal to m into v square by 2s. This is the formula for force. Also you can find out the value of work. So work done is equal to force into distance. So we can substitute the value of force here. So after substituting the value of force you will get mv square upon 2s into s. After cancellation s, you will get the formula W is equal to 1 by 2 mv square. Now this work is equal to the kinetic energy of the system. So this is equal to kinetic energy of the body, that is W is equal to half mv square. Okay. You can find out the same formula by using the alternative method also. So let us discuss the alternative method. The formula for kinetic energy of body is also obtained by this method of calculus. We say this method as alternative method. For this purpose let us assume some physical quantities like m is mass of the body, u is initial velocity, and if body is initially at rest, so u can be taken as 0, f is force applied on the body, and ds is the small displacement produced in the body in the direction of the force applied. So small amount of work done by the force is dw is equal to f dot ds. Since f and ds are in same direction, you can write f ds. Okay. Now if acceleration produced by the force, then from f is equal to ma, this is the relation of force, we can write a is equal to dv by dt like this. Now you can use this value of force in this equation of the work, that is dw is equal to f ds. So let us substitute the value of s in this equation. So dw is equal to m dv upon dt into ds. Okay, and it will be equal to m ds by dt into dv. Now this one is equal to v, so dw is equal to mv dv. Okay, mv dv. Now total work done by the force in increasing the velocity of body from 0 to v is given by, so w is equal to 0 to v m dv. W is equal to 0 to v m into v dv is equal to, since m is constant, you can integrate this equation. This is m v square by 2, or w is equal to 1 by 2 mv square. So this is the formula for kinetic energy by using the calculus method. So you can see thus kinetic energy of body is half the product of mass of the body and square of velocity. You can say magnitude of velocity. So this is the kinetic energy, this is formula for kinetic energy. So you can calculate kinetic energy of body if you have mass and the magnitude of velocity of the body. Okay, this is also scalar quantity, so there is no need of direction. Now let us find out the relation between kinetic energy and linear momentum. Okay, so for this purpose let us consider the quantities like mass of the body is m. Okay, mass of the body is m, u is initial velocity, v is final velocity, or you can take constant velocity v here. So let us assume these physical quantities. These physical quantities will help you to find out the relation. So let m is mass of the body, v is velocity. We are considering that the particle is moving with a constant velocity v in this part. So linear momentum of the body is constant, and that is P is equal to m into V. So, and the formula for kinetic energy is 1 by 2 mv square. Okay, now you can multiply and divide by m in numerator and denominator, so you will get 1 by 2m m square into v square. Now you can see in this bracket this quantity is p square, since p is equal to mv and it is m square v square. So you can write kinetic energy is equal to p square by 2m. This is the relation. Okay, so this is an important relation. It shows that the body cannot have kinetic energy without having linear momentum, and the reverse is also true. It means if a body has linear momentum, it must have kinetic energy, and if it has kinetic energy, it must have linear momentum. If a body does not have linear momentum, it surely does not have kinetic energy, and if there is no kinetic energy in the body, it is sure that there is no linear momentum. Okay, now you can see from this equation, if P is constant, so kinetic energy is proportional to 1 by m. You can see this one is the relation, so you can say K is proportional to 1 upon m. This is equation like y is equal to 1 by x type. So this one is a rectangular hyperbola, and this is shown by figure number A. I am going to show you the graph for this equation. And if kinetic energy is constant, then you can see here that p square is proportional to m, and you can see this is the equation of the parabola. Okay, so let's see the graph for these equations. So you can see the graph A. This one is graph for rectangular hyperbola. In this case, K is proportional to 1 by m. In figure B, you can see this is the relation between momentum and the mass, and you can see the relation P is proportional to under root m. This shows the parabola. Next, here in figure C, you can see kinetic energy is proportional to P square. This one is again a parabola. So these are the graph when between K and M when P is constant. This is the graph between P and M when K is constant. K means kinetic energy. This one is the graph between K and P where M is constant, means mass. So these are the graph. Now we are ready to study work energy theorem or work energy principle. So let me give you the statement of work energy principle. According to this principle, work done by net force is displacing a body is equal to the change in kinetic energy of the body. So you can see here, according to this principle, the work done on a body is equal to the change in kinetic energy. It means you can write W is equal to K final, that is final kinetic energy, minus K initial. Okay, so this is the statement of work energy theorem. Meaning of this theorem is this: when a force does some work on a body, the kinetic energy of body increases by the same amount. Conversely, when opposing retarding force is applied on body, its kinetic energy decreases. The decrease in kinetic energy of the body is equal to the work done by the body against the retarding force. Thus, according to work energy principle, work and kinetic energy are equivalent quantities. Okay, So you can see here, this is the meaning of this statement. Let me repeat the meaning. You can see when a force does some work on a body, the kinetic energy of body increases by the same amount. And you can say, in other words, it means in converse process, when an opposing retarding force is applied on a body, the kinetic energy decreases, and the decrease in kinetic energy of body is equal to the work done by the body against the retarding force. So thus, according to work energy principle, work and kinetic energy are equivalent quantities. We are now ready to prove this work energy theorem. So to prove this work energy theorem, let us assume the quantities like m is mass of the body, u is initial velocity, f is force, a is acceleration, v is final velocity. So since we need these things to derive this formula, so we are considering these quantities. Now the small amount of work done by applied force on the body is dw is equal to f ds, when ds is the small distance moved by the body in direction of force applied. Okay, so this one is the small amount of work done by the now f is equal to m into a. Since we know that a is equal to dv by dt, so we can write dw is equal to f ds. Okay, now we can substitute the value of f here, and you will get m dv by dt into ds. This dv by dt is becomes this dv by dt, so you can write m dv into ds by dt, and this ds by dt becomes v, so it is mv dv. Now total work done by applied force on the body is given by total integration. It means from integration from initial value to final value, mv dv is equal to m. Since m is constant, you can integrate this v dv, since v is variable here. So after integration you will get v square by 2, and after putting the values of initial and final velocity, you will get w is equal to 1 by 2 m v square minus u square. Okay, now half m v square is final kinetic energy minus half m square is the initial kinetic energy. So you will get here half mv square is equal to k final kinetic energy of the body, and half m square is equal to k initial kinetic energy of the body. Okay, so finally w is equal to k final minus k initial and equal to increase in kinetic energy of the body. So you can say work done on the body is equal to increase in kinetic energy of the body. Okay, so this is the derivation of work energy theorem, or you can say work energy principle, right? So I hope you understand this concept, and you are advised to solve some questions based on this topic. So it will be beneficial for you, and it will give you more deep concept of the theorem. That is, I am talking about the work energy theorem. Now you can see the concept, that is potential energy. So let's see what is potential energy. The potential energy of body is defined as the energy possessed by body by virtue of its position or configuration in some field. So due to position or configuration, the body possesses some energy in some external field, and that type of energy is known as potential energy. Okay, thus potential energy is the energy that can be associated with the configuration or arrangement of a system of objects that exert force on one another. Obviously, if configuration of the system changes, then its potential energies changes. So the energy possessed by object due to its position or configuration in some external field is known as potential energy. Okay, so there are two important types of potential energies are here. First one is the gravitational potential energy, and second one is elastic potential energy. Okay, so we are ready to understand the concept of gravitational potential energy and elastic potential energy. So let's see what is gravitational potential energy. Gravitational potential energy of the body is the energy possessed by the body by virtue of its position above the surface of the earth. So that is the gravitational potential energy is energy possessed by any object which is in the gravitational field of the earth. It can be at some height. Okay, so you can see here gravitational potential energy of the body is the energy possessed by body by virtue of its position above the surface of earth. Now we can find out the value of gravitational potential energy. So for this purpose, let us suppose m is mass of the body, g is acceleration due to gravity, h is height through which the body is raised. So you can see in this picture, this is the initial position of the body and this one is the final position of the body. The body is raised by the height h. Suppose its mass is m. So the potential energy possessed by this body due to its presence in the gravitational field of the earth. Okay, so this potential energy in the body is equal to the amount of work done to raise this body at this point. It means height h from the ground level. Students, we will discuss this topic in next class. Thank you for watching.